jump into code. And I'm going to keep an eye on the chat, so feel free to ask questions as I go. I know there's quite a few people in here, so I may not see all the questions. So feel free to ask it again if it's something I don't answer. I'm not trying to ignore it. I see someone ask a question, where are the links to the slides and resources? I'll share those out in a second. Those can also, I'm sure, be shared out afterwards at some point. But the notebook that we're going to be working in has links to everything, and everyone's going to get that notebook. And then links are at the bottom to all the resources we talked about. All right, so let's get started. Welcome to kind of intro to computer vision. And what we're going to do here is build an object detector. Someone in the chat just asked, where is that notebook? I'll share it out. We haven't gotten to it yet. And again, all right. So setup, people have asked about setup already too. We'll be using an online data science coding environment called Google Colab. To follow along coding, you just need a modern web browser like Chrome, a Google account. Colab is a tool made by Google, so to save your work, you'll need a Google account. And then optional, you'll want to download a labeling tool like Hyperlabel is what I'm going to use, and that's how you can actually label your own data set. But you don't need to label your own data set just for this workshop. We're going to walk through how to do that and then use a pre-labeled data set, because labeling can take a little bit of time. But after the workshop, you can then use a tool like Hyperlabel to label your own data set and make your own object detector. Real quick, what this workshop is. This is a friendly, or hopefully a very friendly, introduction to computer vision, and specifically object detection. There's not really any previous experience expected, but knowing some Python can probably be really helpful when we get into code. But I will be describing what is happening there. So we'll cover kind of applications and basic intuition and slides, and then how to label your own data set, and then jump into the code and train a model with it, and then actually run it on a video and image. You totally can't learn everything in 2 hours. At least I can't. If you can, I think you have a superpower. But hopefully you can learn enough to get really excited about computer vision and see that, you know, even if you've never done this before or you don't have a ton of coding experience, you can build something really powerful in computer vision and start solving really complicated problems. So parts of this may feel fast-paced or challenging. That's totally okay. I think you'll learn a lot by sticking through it. And you know, you can also connect with me and ask me any questions afterwards if something didn't quite make sense or you want me to help you with anything. And then the most important thing really is to keep learning after this workshop, right? This is going to be kind of a 2-hour crash course, and there'll probably be some gaps that you'll want to fill in, as well as like some more advanced content that you'll want to go to afterwards. Again, thank you to AI Camp. So they're hosting this event, and I think Bill already linked to these, but I'm just going to throw these in the chat again real quick. So they have a deep learning for computer vision course. If you go through this and you're like, wow, I really want to do computer vision, and you don't have experience with it before, this course might be really good for it, because it's going to cover more of the stuff that we're going to brush over today, like the deep learning and like classification part. And the teacher looks really cool from that, who's I think an engineer at Google. A little bit about me. My name is Sage Elliott. I'm a machine learning developer evangelist at sixskill.com. We do really cool stuff with machine learning, and specifically a lot of stuff around computer vision, and both in like a consulting side, like building models and solving problems for customers, but we also make tools to make it easier for everyone to do AI. Like our mission is to make AI available for everyone. For about the past decade, I've worked as a software or hardware engineer with multiple startups and agencies in Seattle, Washington, or in Melbourne, Florida. And I really love making things with technology. You can connect with me, Sage Elliott. If you Google me, you should be able to find me. But also on LinkedIn, you know, search for Sage Elliott, 2 L's and 2 T's. Twitter, I'm at Sage Codes.
Hey Sage, I see you post a message to all panelists. I think you need to post to all panelists and all attendees. Yeah.
Gotcha. Sorry about
Otherwise,
that. Otherwise,
only 2 of us can see that message.
Those are the links I shared.
Okay, great.
Did that show up for everyone?
Yeah, I think they can see it now.
Okay, cool. Yeah, thank you for mentioning that so much, Bill. That would have sucked later on when I shared the notebook. All right, awesome. Setup repeat for anyone who just joined. Just wanted to say, again, just the setup. We're just going to use a modern web browser and an online tool where we can do deep learning and even access the GPU to do that. So you'll just need a Google account, and then you can download Hyperlabel, which I'll talk a little bit about later. All right, so first question, what is computer vision? It's a really big field, but it's really simply, I would boil it down to, how computers gain understanding from images or videos. And there can kind of be other data types that get lumped in that field too, like LiDAR from like a self-driving car. And then also you can think about audio can often be turned into something like an image, seeing, wavelengths of audios. You can actually use the same kind of methodology we're going to use here to do certain things like, like a sound detection or something like that in audio. So you can see here, here's a little video clip, and we have a computer vision algorithm running where it can detect trucks, and not only just the bounding box around where they are, but also exactly what portion belongs to a truck, and then in this case, if one is moving or not. So it's kind of taking a whole bunch of things from this image and extracting some information, and then kind of understanding what we trained it on. Why I love computer vision. I think it's a really amazing interface into the world, and we're already doing amazing things with it today. So like there's a lot of really cool fields in kind of AI, narrow AI, like NLP, natural language processing, understanding how, speech and generating stuff. But I think there's just so many really interesting applications that are live today in the world, and we're going to talk about that in a second, that you can do with computer vision. Who uses computer vision? So more and more companies are using kind of computer vision across multiple fields. Here's just a few examples that you've probably experienced or maybe even or heard of. One of them is I live in Seattle, Washington, and we have a really small, local company called Amazon. If anyone's heard of them, maybe Amazon.com. And in the chat, let me know if you happen to live in a place. I know that's not everywhere yet, but here in Seattle and some other states, and I'm not sure if they have any globally yet, there's a store called Amazon Go. Has anyone been to one of those before? Someone said yes. Awesome. Yeah. So if you go in there, it's really interesting. You go in, there's no lanes for checkout. There's no cash registers. It's all computer vision based. I don't think they even use sensors in their shelves. I could be wrong on that, but I think the goal is you have a store that's 100% computer vision based. So you walk in, you look up, it's all just like arrays of cameras, and I'm assuming some sort of like edge GPU for computing up there. And I can walk in, I can grab a drink, I can grab food. There is one near me that's actually like a whole grocery store. You can even rummage for the fruit you want. And then you walk out of that store and it charges you for what you picked up solely based on computer vision. And it feels like you're stealing the first time you go because you scan a QR code as you go in. That's it. Otherwise, you just walk out. You don't have to talk to anyone. You don't have to stand in line. It's really cool. And then obviously they're using for things like delivery robots. Amazon recently, I think, bought a self-driving car company, so it seems like they're probably getting in that field. And then, so they actually also use computer vision to look at like product listings, like images for products, to try and flag things that could be fraud. Google Photos, you probably, if you have a Google account, use Google Photos, you'll see something like you could search for a dog and it'll automatically find all the dogs in your photos. YouTube content filtering, and self-driving cars, Tesla self-driving cars, Facebook face tagging. I'm sure they use computer vision in many other applications, but these are ones you probably heard about or seen before and actually used. But some other computer vision applications, and this is actually kind of what gets me really more excited about computer vision. Like all the stuff that big tech companies are doing is really cool, but there's also so many different fields that you can use it in that a lot of people don't always think about, right? Like a lot of people think it's about self-driving cars or something like Amazon Go that these big tech companies are doing. But really almost every field you can think of, at least where there's some sort of visual aspect to it, you could use computer vision to start solving problems. So like healthcare, X-ray and MRI diagnostics, kind of like drug and medicine research, manufacturing, quality assurance. This is actually how I originally got into machine learning and computer vision, was building something that could do a better job of making sure that a part we were manufacturing was where we needed it, quality-wise. Oil and gas industry, you could do like leak detections and safety. Agriculture, which I think is a really cool industry, like crop monitoring, animal monitoring, construction, site monitoring for safety, like are people wearing hard hats and stuff. I've seen people working on self-driving tractors. And then you can do really cool, interesting things too around like generative AI, where open this up real quick, where you can use something called a GAN and generate images that aren't real. Like none of these faces are real faces. They were trained on a large data set of real faces. And then they use something called a GAN, which can create realistic looking images. Any questions so far in the chat? Like, what fields do you think would be really interesting to apply computer vision for? I think it's really fun to think about like what problems you can start solving. You can let me know in the chat. I'll wait a second. All right. See one in the chat. I see a couple questions in the Q&A. I'm going to look at those real quick before we move on. Someone said, saw 6 skill has a lot of edge AI solutions. Are there already object detection image segmentation models who can run on mobile phones or edge devices without a GPU? There are some models that you can do that for. You just have to be really selective around them. So oftentimes deep learning and like computer vision models can be pretty computationally expensive, but there are ways of making like smaller versions to run on things like a phone or a Raspberry Pi or something like that. But it's something to think a lot about. So instead of applying AI to healthcare is also interesting. Yeah, very interesting field. Cool, seeing all these things, migration monitoring, oh, that'd be interesting. Someone said taking over the world, that'd be scary. Someone said we'll be able to download the slides after the talk. Yeah, I'll send the link. Those will also be shared shortly. So I know people are asking for them, but don't worry, they will be shared. Yeah, so cool seeing all these different ideas people have, like identifying repair percent on repair projects, advertising, computer vision healthcare, weather disaster forecasting through satellite images. That's totally really cool use case. Computer vision and law enforcement. Awesome, very cool. Yeah, someone said weapon detector. All these are really cool use cases, and I'm so happy to see so many awesome ones that you're providing in the chat. Motion detection, cool. All right, so I'm gonna keep moving on. You can keep putting stuff in the chat if you want. So computer vision and deep learning often get associated together, and computer vision isn't always necessarily tied to deep learning, but in the past decade or so, deep learning in the field of computer vision has just been like killing it. So anytime you see something that's performing really well, most of the time it probably is using deep learning, like when it makes the news. But I just want to mention that, you know, that's not always the case. Like you can use a library I'll talk about a little bit later called OpenCV, and you can actually do a lot of like image manipulation or doing things like finding edges and stuff without deep learning. So it's not always like deep learning is exactly what you need for it, but most of the time for classification or object detection and stuff like that, you probably will be wanting to use deep learning. In other intros, we'll cover way more in depth, like the deep learning portion. And I'll just share these links in the chat and talk briefly about it. And mainly just keep in mind right now that deep learning is kind of a subset of machine learning where, you know, instead of explicitly programming all the rules ourselves, we feed data into a function or like a deep learning neural net. And then it learns from this data what we're trying to do. So we would, for example, feed it images of cats and dogs. We say, hey, when I give you a new piece of data after you're trained, I want you to predict if this is a cat or a dog. So we would give it a whole bunch of training images. It would tune a whole bunch of different parameters in there. And then we would give it a new piece of data once it's trained, and then it would give us the prediction, in this case, like a cat or a dog. And someone asked for me to share these links, 100%. We'll share these in. So deep neural network, this is kind of the underlying piece of a lot of deep learning and again, like a lot of computer vision. And we won't be going too in depth in this course, in this tutorial, but like I said, almost any other one you're going to go through will cover these way more in depth. And I really want to kind of jump to the part of doing like your own data and building a object detector, and then you can fill in these gaps of like how a deep neural network actually works or a convolutional neural network. And this is a really good visualization. So the go click around and play in this, and we can come back to it later if we have time. But a convolutional neural network is kind of a different type of a deep neural network, and that's actually what we usually use for computer vision. And a convolution just means essentially a filter over an image. So it's applying different filters and finding out what is the best fit for like detecting edges to eventually build up and detect objects. But for now, if you've never done anything with deep learning, just imagine, right, it's something we give data, it learns from that, and then we give it a new piece of data, and it's going to return a prediction. Does that make sense to everyone? I know like that's a very high level concept, but I just want to make sure that that's clear enough. All right. Transfer learning. So with most popular deep learning frameworks, you can load pre-trained weights into your network. And these have been trained on like a lot of objects. So there's several like the COCO dataset and the ImageNet dataset. The COCO dataset has like 81 classes, so something like dogs and random stuff like hairbrushes and people and things like that. And the way transfer learning works is that like when we had this this deep learning kind of function, someone else trained it on a whole bunch of data. And we want to train it on a new use case. So in our case, right, we're going to feed it new data for an object detector. And the one we're going to build, the default data set that we're going to use is a goose. So we'd say, you know, this neural network's trained on a whole bunch of data from someone else, and it learned what, you know, makes up maybe a different type of bird, what makes up a dog, what makes up a person. And we can take all those weights and give it new data. And so instead of starting from scratch, it actually has a whole bunch of stuff it's already learned about the world, like shapes and stuff. And then we give it new data set and say, hey, keep adjusting those weights, but now only predict this new data that we're giving you. In this case, it's going to be a goose. So you can think of transfer learning as a way of not starting from zero. And it's really, really powerful. And most of the time, you're probably going to want to use it. It's a good rule of thumb. So if you're doing a hobby project, like you know, nothing super crazy or anything like that, a good rule of thumb to get started when you're using transfer learning is start with a minimum of 200 images or 200 instances. So an image could have, for this example, like 2 or 3 geese in it or something like that. And you'll want about 200 instances or images for it to start learning well. But it does depend on your type of data. So sometimes you'll need more data. If you don't have the 200 images, you could totally try training without that much and see what happens. And it actually might work fine depending what your data is. And without transfer learning, you would probably need to spend a lot more time and have like thousands of images to get a good result. So again, just keep in mind, this is kind of like, we're not starting from zero. A network's already been trained a lot, and now we're feeding it new data. All right, so some types of computer vision. Computer vision is a really big field, so this is by no means like everything. And we're going to focus on computer vision with deep learning. And a lot of these can be combined together or kind of used with other algorithms outside the exact like deep learning portion to form like various outcomes, like what you need. So we'll talk more about that as we go. So classification, this is where most people start. And you just feed your neural network a whole bunch of images, like I talked about, like a dog and a cat, and then it's going to learn to classify a dog or a cat. But there's kind of a problem with this where, you know, you could have multiple dogs in a image, and it wouldn't know that there's just one dog or 2 dogs. It's just saying, well, I think there's a dog in this image. Or you could have a dog and a cat in this image, and whatever one it thinks is more prominent is the prediction it would return. Object detection. So object detection can classify, but also localize where an object is inside an image or video. So here we have one on goose, or a geese, and it's detecting a goose right here. And it's not just saying, you know, there's a goose in this image. It's saying, well, there's a goose, and I'm pretty sure it's right here. This is where I think this goose is. And in this case, there's another goose. I'm pretty sure it's right here. So it can actually give coordinates of where objects are in here. And it's really powerful because you can actually start doing things like, you know, counting how many are in there, object tracking, are they interacting with each other, which is really cool. And this is what we're going to make today. And we'll cover how to make your own data set for this. you have instant segmentation. So it's kind of similar to object tracking, except for instead of just drawing a bounding box around it, you actually draw pixel-wise what you think is that object. So here, we're detecting the bottle itself, not just, you know, square around the bottle. It's like the actual bottle. And then we're detecting the water inside of the bottle. So you could then use this to like do measurements of like, well, how full is the bottle of water? It's also really good if you need to be a little bit more precise. So we'll see a video in a little bit, but if you want to see if like a hand is touching something or something like that, you can use polygons because they're much more precise and they see exactly where the thing is in the pixels versus just a bounding box of where the entire object is. Feature point clustering. So in this case, we'll use this to detect kind of postures of people. And they're detecting kind of the pose of a yoga class right now. But you could use this for like behavior monitoring for different animals and things too. It doesn't just need to be a person, but how is like something walking or leaning or, you know, what's happening there. You can also use it on faces. So not just like a whole skeletal structure, but also, you know, like what is a mouth doing? So it's really common to do something for like moods and expressions. Image captioning, so you can actually train neural networks to understand context in images where you could feed it this image and it wouldn't just do classification like, you know, there's a kite, there's a girl, there's a beach or anything, and it can actually understand some context around images. So it could say something like, there's a child flying a kite on a tropical beach, which is really interesting. GANs, so we talked briefly about these when we saw those like generative faces. Here's a little bit more simpler example. This is one that I made with a colleague, and we were training it to create new architecture designs based on like a famous architecture designer. So we'd feed it images, and you could go read more about it in that link I just shared in the chat. But this output here is actually, so this is during the training for creating like buildings, and these don't look like buildings at all, but I thought it looked like really cool art. So a really fun thing about generative deep learning and computer vision is it'll just make really interesting things before it you know, gets to where you want it to, or it may never get to where you want it to go, but you'll have like really interesting art pieces come out of it. Same with if you do it for sound, it always makes like something funny happens. Choosing a model. So there can be many, you know, use cases for different models and ways to tie them together. But when you're getting started, just think about like, what is the problem that you're trying to solve and what is the outcome that you're looking for? So in this case, we're doing image segmentation again, or object segmentation. So we have this mouse labeled, right? You can see pixels are drawing over it. It's pretty accurate. The ear is out a little bit, that's okay. And then we have a piece of food where it's also pixels are drawn over it, not just a bounding box. And then here we have, you know, something outside of our deep learning model that we can say, well, when this, you know, polygon, these pixels of the mouse are interacting with this piece of food, we can then say, you know, that it's feeding, or that's interacting with food in some way. So you can think about, you know, if you need to do something like this, like actually understand pixel-wise where something is in an image, you can do image segmentation. I like to talk about building that too, because it's not that much different than building our object detector. So if you have that as a use case after this workshop, you should be able to build that as well. Any questions so far on those different types of models? You can also, instead of just in the QA, you can also just type directly in the chat. Give you a second if you have any questions about the different types of computer vision that we just talked about. Is there anyone that you find like the most exciting that you're interested about now that maybe you didn't know about? Someone asked, is the Google Cloud certification useful? I don't know. Probably depends on what you're looking for. So is it image segmentation is definitely exciting. I think it's really cool. So instead, if you have to object detect something more specific, do you have to just create your own data manually? Yeah, so, and that's where, well, create your own data manually. There's different ways of doing that, but yeah, so like I'll actually show you like my data set of a goose, and I actually created that manually. I just went to a park and took photos with my phone, and that's really all you need to get started. So if your example, you asked, you know, like parts of a lamp, you could take pictures of a lamp, and then there's different ways of labeling it. In this case, we could do like image segmentation or object detection of like, this is the knob of the lamp, this is the shade of the lamp. And you can actually train a model, I think, pretty quickly on something like that. Yeah, I'll try to keep that use case in mind, like the lampshade, when I show the labeling. Someone said GANs are really interesting. You notice NVIDIA used it recently to compress video images. Yeah, I saw that recently too. So they actually use a GAN, and instead of just compressing videos the normal way, they, I think, use a GAN to do it, and it's like 1/10 the size of a normal compression Kodak or something. It was like pretty crazy, really interesting to read about. All right, cool. I'm going to move on if that works for everyone. All right, so object detection in a gist. So there's different object detection models, and I'll actually share way more links later. When we get to the code part, like I was saying, all the links are actually going to be in that notebook at the bottom. And I'll just share this in here though too. So there's different types of object detectors that you can use, but kind of in a gist, what they do is they'll find proposed regions of where they think something is, and there's different ways of doing that. So it could just be looking for like edges, contrast to the background, being like, well, I think there's some sort of object here. We might want to look over here. So in this case, you know, maybe it came like 3 places. It's like, well, I think there's something here, here, and here, even though there's one, but it isn't using like deep learning yet. It's just saying, I think there's something interesting here we should go look at. And then it runs a classifier around that region. So, you know, it's our model's trained to understand if it's a goose or not. It would run like a classifier around those regions, say, hey, there is a goose here. And then it would use some math and kind of draw where it thinks that goose is based on kind of like the proposed region I returned. And again, like I'll share more links more specifically to the different ones later. So popular detection methods, you have single shot multi-box detector, abbreviated to SSD. So that can do object detection like the bounding boxes, and it's pretty fast. And then there's another one called YOLO, which is really popular. I think a new version just came out. I haven't really looked at the benchmarks on it, but I think it's also really fast, and also can do object detection. And YOLO stands for you only look once. And then there's a mask-R CNN, or faster mask-R CNN. And this can do the object detection, image segmentation, has really high accuracy, but it tends to be a little bit slower and computationally heavy versus some of the other things like single shot multi-box detection. So, you know, that's something to keep in mind. Someone was asking about edge devices earlier. You might not be able to run a mask-R CNN on your edge device depending on how much compute power it had, but you could probably run a smaller model of like a single shot multi-box detector. So you can keep that in mind, you know, where are you deploying this thing afterwards? And then we're going to use something called Facebook Detectron 2. It's a really cool library maintained and created by Facebook, and it actually is a fork of mask-R CNN. So it can do all those things like object detection, image segmentation, and more. So here you can see a little preview. It has object detection, skip ahead. It does, you know, pose detections. We talked a little bit about that too. This is called dense pose, where it can actually draw like a 3D kind of a map around those feature points, which is really interesting. And then it has image segmentation. So right, it's seeing like there's a table here, there's bowls on it. This is really good for understanding a little bit more context of the world. And then they have this version as well, where not only does it have the instances like a table and cup, it also has the background. So if it was outside, you know, you could be like, this is the sky, this is a road, you know, and actually have a little bit more awareness of where objects are in the world. So it can do a lot of really cool stuff. It's a really powerful library, and it's fairly easy to get started. And that's where we're going to use today. But all the kind of ideas that we're exploring today, you know, they can be used across different libraries as well. So you can learn how to do it in TensorFlow and Keras and PyTorch, and they all have different methods of bringing in pre-trained models. But we're going to use a Detectron 2. Oh, I'll share this link in the chat too if anyone wants to see it. All right. So I just want to briefly mention kind of the full computer vision lifecycle too. So what we're going to focus today on is data annotation and labeling. So, you know, how do we make a data set to give to a model so it can learn what objects are and how to detect them? But often there's a whole bunch of other stuff that people don't always think about. So like you might have device management. Again, this is something we work with. Like someone asked about 6 skill in edge computing. So we can actually manage edge computing resources like, you know, a Jetson Nano or some sort of NVIDIA device with edge computing, as well as sensors. So like collecting the raw data is something people don't think about a lot too, because you might already have a data set or be given a data set, but how do you connect like a camera stream and start getting that data? And then how do you, once it's collected, how do you manage that data and create data sets? And if you weren't doing it from a live camera feed, one thing you could do is like scrape the image or scrape the web for images. And then you have data annotation, where you actually do the labeling. You have the machine learning, you know, selecting the model for your problem and the actual training. And then after that, a big thing too that kind of people forget about sometimes is deployment. So once you have your model, how do you then get that model into the real world doing things? And there's a whole bunch of different ways of doing that as well. And then a lot of times for real applications, you kind of want to repeat these steps to make sure your model's always performing well and giving it more data. Typically with deep learning, the more data, the better. So you can be running all these things and collecting more data from your camera stream and then labeling that data either yourself or using some sort of ML assisted labeling, and then just keep making your model better and better and working across more varied data. And we do all that in one platform as 6 skill. And if you're just interested about that at all, feel free to let me know or check it out on there, request a demo, you can email me. But kind of like if you're just interested about like what does that look like in one integrated platform, let me know. All right, real quick before we get into the labeling and the actual code itself, there's just some popular libraries used for computer vision I want to mention. There are many, many of them, but these are the ones that I kind of use probably the most, and that you'll see the most when you get started. So you have PyTorch, which is a library from Facebook for machine learning, very popular in deep learning. You have TensorFlow and Keras. This is kind of Google's version of PyTorch or vice versa. They do very similar things. You'll probably start with one of these, and then you might want to just look at the other one just to see how it works, or if a specific job uses one, maybe you learn enough about it before you go in for an interview. But they're very similar to each other, at least in like what they actually do. And you have OpenCV. It's a really awesome open source library for image processing and computer vision. And then you have NumPy. It's great at processing and manipulating multi-dimensional arrays. And that's actually what images become to computers. So when they look at an image or a video feed, you know, they actually just see a bunch of numbers or arrays or lists in Python, if you're familiar with arrays. We can actually look at what that looks like when we get into code. If you want, we can pull up an image and print it out as an array. All right, so let's get to image labeling. And again, I'll share this link. So I'm going to be using Hyperlabel, and a lot of these concepts will work on any other labeling tool. Ours is a very nice labeling tool. I mean, I might be a little bit biased, but there's an open source one called, I think it's Label Image. I always reverse if it's image label or label image, and it's an open source one. I think it works across all platforms as well, but it's not quite as nice at like organizing and exporting in different formats. And labeling is a huge part of computer vision. A lot of tutorials don't bring that up, or kind of like just mention it briefly, you know, giving you a pre-labeled data set. But it actually matters so much how you label, and there's a lot of factors to think about it. And I will share, this link is to a previous talk I did, and it goes more into like how to think about data specifically and even overcome limitations with your data set. So someone asked about like creating your own data. For this example, and we'll see this when we look at my Goose data set, this actually talks about, you know, having very limited examples. How can you overcome that? Creating your own synthetic data. So I Photoshopped pictures of geese into different situations, and I can talk about that a little bit later. But for now, I'm going to open up Hyperlabel. And so this is what it looks like. This is kind of just the homepage project directory. And I'm going to show you how easy it is. Because again, when I was doing tutorials, I was so frustrated that no one like showed me how to create a data set easily. And we make it really easy. So you can hit create project. And I'm going to call this geese demo. Call it whatever you want. I'm just going to hit next. And then in this case, I have all my images just in a local folder, but you can connect to things like Google Cloud Storage or Amazon S3 buckets, or have them organized in a local CSV. So I'm just going to hit local storage. That's where we just have a folder of images. You can name this. I'm going to call it initial geese. So you can actually add multiple local like sources or multiple sources into this. So like this one could be like my initial geese data set. And then if I collect more data later, I can have that in another folder and then add it in and then continue labeling. So I'm going to choose a folder. I'm going to hit geese small. I'm just going to hit save. And then I go to this label schema button. And then here's where you're actually selecting what type of label you want. So remember, we talked about like image segmentation. Well, to label things like that, you would use polygon. If you're going to use feature points, you would use feature point. And then text and select is also another term for like class or classification. So what we're going to do is let's create a schema for a goose. I'm just going to say goose. We're going to say it's a rectangle. We're going to train for object detection specifically. So it's going to be drawing the bounding boxes around it. And you can change the color. This is really just for you. If you're doing a lot of labels, you might want like different colors so you can see it more clearly when you're creating them, but it doesn't actually affect anything. So I'm going to hit create. And now it's here. I'm going to go ahead and delete. These are kind of sample ones. So when you first get started, you can see some examples of how they work. So we have this goose one. I'm going to go ahead too. I'll create a goose polygon label just so we can look at what that looks like. Like I was saying, I'll show you how to do both of these, and then it's up to you afterwards, like what kind of data set you want to create and label. All right, so we have two. We have goose for rectangles, and then we also have a goose polygon. And I'm going to hit start labeling, and then this will bring up the images that we added. Actually, just skip a few. So I can talk more about that talk we have later. Time later, but there's some geese that are photoshopped, and that's about kind of overcoming some of those limitations of like not having enough goose photos. So here's a real picture of a goose, and I want to label this for object detection. So I'm going to make sure that my rectangle is selected. It is by default the first one selected, and you get these nice little crosshairs to show you where you should start labeling because you want to draw a rectangle around it. So I'm just going to go ahead and do this, and boom, done. And you want to be, as close as you can to the goose typically, but it's okay if you have a little bit of room outside, especially for, just kind of like a hobby type project or something. If you're not trying to get the top accuracy, just something like that is fine. Once you label that, you can just hit submit. And you would just want to do this for all the images in your data set, or all the ones you want to use to train your model. And one important thing to note is that when you're doing things like object detection or image segmentation and you're labeling your data set, you want to make sure that you label every instance in your photo. For example, if I only labeled one goose here, the model would have a really hard time understanding what is a goose, because I'd say this is a goose, and then when it's learning and we feed this in as training data, it's going to make a prediction and see how it did on this photo. So if it predicted that this was a goose, but also this was a goose, and then looked at our labels, we would see that, we said only this one was a goose, but it'd be like, well, these features look so similar, I'm going to have a hard time understanding what a goose is. So anytime you're labeling something for object detection and there's multiple instances in that photo, you want to cover all of those instances. And then I'll show you real quick what you can zoom into. I'll show you real quick what labeling like a polygon looks like. So we'll just click this polygon. And this is essentially drawing. I'm going to do a very bad job here. I'm just going to show this really quickly. Drawing a polygon label around a goose. You'd want to do a little more accurate than me. but you can get the gist, right? Like you're drawing not just a bounding box, but exactly what the goose is. And I think in here too is if you did mess up a little bit, you can click on this and kind of bring it in a little bit, so you can get really accurate afterwards. So this is how you would do the image segmentation. Just do this for every instance. But you can see that like I drew that really fast and kind of poorly. Labeling polygons takes a lot longer than a square, right? So something to think about too. But polygons are generally provide more accurate predictions. So if you're in a use case where you're like, I need my model to be more accurate, you're just not getting there with the bounding box, you might want to do that with a polygon instead, and that could increase your accuracy. All right, let me catch up on questions. Let me know, do you have any questions about labeling real quick? Actually, real quick before I catch up on questions, I'll go ahead and just say, so you would submit all these images, hit submit the ones you're done with. And then, oh yeah, someone said in the chat, sorry, I can't follow along. You don't have to follow along, I'm just showing you so that once you're done with this, then you can download this and label your own data set and then put it in the Colab that we're going to use. So don't worry about following along on this step. So once you're done labeling, you just hit submit on all those things. Then you could go to dashboard or review and hit export labels. And then you get all these different formats to export it to. So this matters for depending what model you're going to use. In our case, Facebook Detectron 2 and a lot of the object detection libraries will use either Coco or Pascal VOC. We're going to use a Coco data set today. So if after the workshop, you're going to create your own data set for this, just go ahead, import it. And then once you're done, you can hit export. And I'll just say, go in this goose folder. And then what that did is it just made a new, folder, and, oh, sorry, it's called Goose Coco, or it'll look something like this. So you'll have a folder, and then you have images in the separate little image folder. And then you have something called instances. And this is actually the JSON that will tell your model what is a goose and what isn't a goose. And we'll talk more about getting this into a model when we actually train one. But that's kind of like pretty quick overview of labeling. Does anyone have any questions about that? It's I just want to make sure it's clear that it isn't super hard to create your own data set. It can take time. But if you use a nice tool like this and you have like saved projects, you can always come back to it. We're also working on some new features that will be coming out soon that use AI and machine learning to assist with labeling. So instead of drawing a polygon around a whole goose, which can take a long time, we could do something like just draw the bounding box. And then once we draw a bounding box around it, automatically do polygon selection there, as well as like using AI machine learning to already understand what, in this instance, what a goose is, and then apply labels to it. All right, now I'm going to catch up on the chat real quick. I see some questions in there. Just let me know in the chat if you have any questions about labeling. And again, this was on Hyperlabel. You go to hyperlabel.com and then just download. We don't have a Linux version out yet, but we have a new version coming out soon. Hopefully later this month. If not, it'll be early November. And it's actually going to be web-based, so you can use it on anything, which will be really cool. I'm excited for that. All right, I'm going to catch up on chat. So what someone said, what if they hired like 10,000 people to label? Yeah, that's actually, so like labeling is actually a business right now that people pay for, and you have someone that can go through and label stuff. Someone said, does the image orientation, portrait, landscape, and image size matter? Does it need to come across? Does it need to be the same across all images in the input data? Great question. So the orientation, I would say it matters for like what your problem is, right? Like if you're never detecting cows walking upside down, then you probably don't want to train your model on that, and it'll be more accurate of just like, of them in the right orientation. So I would make sure that they're all flipped the right way. I mean, it might work okay the other way, but I would just make sure that you're training it on a better representation of how it's going to see what you're labeling in the real world. As far as image size, so almost all the time for any like convolutional neural network or deep learning computer vision application, they'll actually compress the image during training. So you can have a large image, but it will compress it down to something like 244 pixels by 244 pixels. And so the actual size in here doesn't matter as much, but it's something to keep in mind too, that I actually usually like to do if I'm training something is I'll resize all my images to a smaller size, like something like 800 by 600 pixels. Just even though the resizing will happen during training, it still has to load the full images into memory to load into your model. So if you have a smaller image before the training actually happens, it can speed up training time just because it still has to load the whole image in memory somewhere. It's a great question. So said, do polygons help with text recognition as well? Yeah, so you could do something like labeling specific characters and recognizing a T or an H or an E. That could be one way of doing it. There's actually like a whole subfield that's in computer vision called object character recognition. And I think there's a lot of other ways of extracting text versus training a model just on every single character. So I would look into that if that's a problem you're looking to solve. Someone said, what if they created Wikipedia of labels with bounding boxes and polygons in open source format? That sounds awesome. And there's actually a lot of stuff kind of like that. And there's probably more than I even know about, but like the Coco dataset, for instance. And this is what, like I was saying, a lot of object detectors come with a pre-trained version of this. When we use transfer learning, we're using something from this. And it's here, let's see, it's 330K images over 200,000 labeled. And if you look in here, I forget all the classes, but there's 81 classes, and it has things like people and cars and trucks and stuff like that. So you can get something to detect an object generically. The problem with that though is, like let's say this did have a goose. It doesn't. It might have a bird. But let's say it had a goose, but it was never trained to detect geese in whatever situation I'm detecting geese or at this exact angle. So it'll do an okay job in certain situations or a good job in certain situations, but it might perform really poorly in other situations. So it's important, like, and we do this a lot where we're getting data directly from the problem that we're trying to solve and then label it in that context. And computer vision models will generally work a lot better. But that's a really cool idea. I mean, if you make something like that, let me know. Someone said, could we extend hyperlevel beyond the visible spectrum of light? So that's a great question. And that's really a little bit more on how you're collecting your data. Like what is that camera device? What can that do? Because as long as you can see something in hyperlabel, you can label it. And there is cool features where like you can change saturation. So if you have something that's harder to see in general, you can do stuff like this. But that really comes down to like the device collecting the data. And so we actually do applications like that where we use infrared cameras, and that's beyond our visual spectrum, but we have a camera that detects it, and then you can see it in that image and then label it. And in some cases, we even do go further than that and use computer vision to make that easier to see, like if there's movement, like add colors and stuff to it. So it is really cool. But that's a great question too, but that would go down to really the device collecting the data, not necessarily the labeling tool typically. So what does text do? Read text and images. So actually, if you look at the same Coco data set, they all also have text labeling. So like you can add what that caption is, and then you train a neural network, and you don't just throw it into a convolutional neural network. There's a little bit more to it typically. So you use something like a transformer or a recurrent neural network in combination with like a convolutional neural network, and it can combine computer vision with a little bit more context understanding. So you can actually train, on this image, and it would understand that there's a beach in it and pick up what that is, and a child and a kite. But that's a great question because it's not as straightforward as the other labeling or as the model we're going to use today. Someone said, labeling seems like a manual intensive task. Can machines perform labeling too? Yeah, so that's where I was talking about how we're coming out with features for that to make labeling a lot easier. So we could do something like you label a few images and it understands what you're looking for, and then it'll just automatically keep adding labels into all those things, or even the rectangle of poly and stuff like that. So it's a really exciting field to me because, like I was saying, labeling data is so important, and a lot of people don't think about it all the time. But if you can come up with a tool to make that easier, you're going to make computer vision accessible to way more people, and then also just save a bunch of time. So it's about how would the labeling machines recognize what they need to do. So yeah, you need to typically train them in something first before they can apply a label. But you could do it on some instances and then automatically do it. Looks like someone else answered in there. Just like how GANs work. Okay, yeah, just keep talking. All right, cool. So I think I'm caught up in there. And let me look in the Q&A real quick. And if you have any other questions about labeling, let me know. Q&A questions seem to be not working. Like they're just in like random orders to me. So yeah, if you ask something in Q&A and I don't get to it, ask me in the regular chat, because just right now, at least how I'm set up, it's just easier for me to see those questions. And it actually looks like a lot of the questions that were asked in there were also asked in the chat. Oh, someone asked a good question here. What about video? Great question. So we can actually import a video in here too. You would just say, save and submit. You would just say, like, when you add a new data source, so if you want to add another one, go back to project details, add another data source. If you choose a folder with a video in it, it'll prompt here and say, hey, we found a video in there. How many frames per second do you want? So if you have a lot of frames per second in your video, you could narrow it down to say, I only want 1 frame per second from this video. And then they'll be imported as images and show up just like everything else. So it can handle video data labeling, which is a great point. Thank you. So it said for video, do you have to label several frames? Yeah, so right now, without kind of ML assisted labeling, you have to label each frame individually. I mean, you don't have to do every frame for your model often, though. You can skip some because they'll be so similar. But one thing that's cool in here too is, and I didn't show this, so you could have labels here, and oftentimes frames don't move too much, like, the distance between an object per frame. So you can actually toggle this auto add from previous. So now when I go to the next image, in this case, I don't think it's a frame, but I'll automatically have those labels I had. And then you could just click and drag them. So if they moved a little bit per frame, you can do this. And this actually saves a lot of time. I've done this a lot too. Great question, because I totally forgot to mention that too. Cool, so that was labeling, and we're going to jump into code. Does anyone have any other questions before I do that? Real quick. I forgot to share this earlier because I think I skipped a slide, but I have a Slack channel as well that is kind of around these products and these workshops. So if you want to join that Slack channel and ask me any questions, you can do that there. So when hopefully you're going to create your own data set and build your own object detector. I would love to see it. But if you run into any problems along the way, let me know, or just any general questions about computer vision and machine learning. The best place to connect with me is either on that Slack channel or on my LinkedIn. All right, so we're going to go into this code part, I think, if everyone's ready. Is everyone ready to actually go in and train a model, train an object detector? I'm going to share this. Yep, I'm gonna type these in, just making sure everyone's still here. So here, this should bring you to a Colab. And if someone wants to have that or this other link, I'll put them both in there. One is just the bit.ly, because I know sometimes people will be watching from a different screen, like on their phone and typing on their computers. If you want to type in the bit.ly, you can. And then here's just a link that goes straight to it. And often people will join in workshops a little bit late. And if someone wants to keep track of one of those links for me, and if anyone asks for it in the chat, if you want to just share it, that would be awesome. And this Colab will have a lot of links at the bottom too. So like most things we talked about, and the slides should be in there as well. So that should open up this for you. Let me know in the chat, anyone who clicks on those links or opens them up, do you see this environment? This environment, it might look like this. Just give you a minute, because I know it can take a minute to load. Once you're in this environment, what you'll want to do and enable you to change the code and run everything without any errors, go to File and hit Save a Copy in Drive. So File, Save a Copy in Drive. The links to the slides are in that in the Colab at the bottom. Let me just make sure that sharing is on, because if this doesn't work, I'll change it. So if you can't access it right now, after the workshop, I'll change it, and then you should be able to. But yeah, you can have those for reference. And then again, feel free to connect to me if you need them, and if for some reason they're not working or something like that. Connect with me and ask for them. But go to File, and then Save a Copy in Drive. Who saved a copy in Drive, and did it work? Awesome. Someone said me. I'm going to give everyone just a couple more minutes, because I know it can take a little bit. It can take a little bit to create a copy too. So this is creating a copy, and then it should just open up in a new tab. This is your copy saved in your Google Drive. So anything you do here will be saved, but you can always reference this link back so that if you do mess anything up, like don't worry about messing anything up here. You can always come back and get the original copy if you just save that link. So feel free to bookmark it. All right, did anyone not do that is still waiting? People are saying all working, awesome. So you should have a copy, and you should have something that looks like this. All right, so I'm gonna walk through this beginning. If this doesn't work, if it hasn't worked for anyone, just let me know if you get any errors or anything like that. But if you've never used Google Colab before, it's essentially Google's way of hosting what's called a Jupyter Notebook. It's a really popular tool used in data science and machine learning. It's a place where you can write code, documentation, and see like outputs visually all in one place. So it's really, really good for like experimentation and kind of documenting what's happening. To be able to edit code in this workshop, you got to make the copy yourself. Otherwise, I think it'll throw an error. So do that File, Save Copy in Drive. And then once you're in here, you can edit the code or edit the text by just double clicking on this. And you can do this if you want to take notes as you go or anything like that. And you'll get this format here where you can write in Markdown, which you might be familiar with. And to get out of this view, just hit Shift Enter, and then you'll go back to this view. Oh, and one really cool thing, and yours should already be set to a GPU, but you can double check it. So one of the coolest things about Colab is not only is it just like an online Jupyter Notebook, but they actually give you free access to a GPU or a TPU. Both can be used for training like deep learning models. So to get that GPU, you go to Runtime, and then you hit Change Runtime Type. Yours, because you copied from mine, should already have a GPU selected. But if you're doing your own Jupyter Notebook later for deep learning, you'll want to go and hit Runtime, change Runtime Type, and hit GPU, which is really cool. Yeah, it should be Shift Return for Mac. Should be fine. Someone said, what is the GPU? What does it mean? So GPU stands for Graphical Processing Unit, but the way it's made is the type of processing that it does is really good for deep learning, and it runs much better than a CPU, which is your central processing unit, for those types of calculations. So use a CPU and a GPU, and the GPU will actually do a lot of those deep learning kind of math crunching things, and it makes it way faster than trying to train on a TPU, or sorry, a CPU. A TPU is similar to a GPU. A TPU is, I think it's Google owns the TPU, and it's their proprietary like way of processing tensors. It stands for tensor processing unit, because that's actually what you're processing most of the time on a GPU. And so it's their hardware that I think might be optimized really well to work with their library TensorFlow. But PyTorch recently also can run on a TPU now. To get to that, go to runtime, change runtime type, and just select from here. Again, you should already be on it, but I wanted to show you. So if you create your own notebook, you know to do this if you're doing anything with deep learning. So someone said, what's the difference between a CPU and a GPU? Kind of the different types of processes that are good at running at. So a CPU, almost every computer has. A GPU is something like a gaming laptop has, where you can run more powerful graphics on it, but a lot of the same type of calculations that happen in a GPU for gaming, it also does for deep learning. So it's just more powerful at certain types of processes. All right, so this is a text cell you can edit, and code cell. So code cell just looks like this gray cell. And to run the code, so you don't have to type this out, I just want to show. So you could say print, we're going to say hello. Hello AI camp. And then to run it, you can hit this little play button with your mouse, or you can do the shift enter, shift return, and it'll run. The first time you run any code cell, it can take a little bit of time because it's connecting to the server. It's like creating your instance. Once you do it for the first time, then it shouldn't take this long to run a code cell. And there we go. So we said hello AI camp, and our code cell ran. To run terminal commands, so Colab actually gives you access to a whole Ubuntu instance. It's not just some tiny little thing that you have really limited access to. So you can actually do like bash or terminal commands if you're familiar with them. To run that though, you have to put this exclamation point at the beginning. So here we're just going to say, git, if we want to do something like git in GitHub, and you can see that git is installed on here, and we can actually run that terminal command just with the exclamation point at the beginning. You do like ls to list for directory, what's in there. I think right now we might be blank until we install some stuff. Oh no, we got, or you'll have sample data folder. So the exclamation point, that is just saying that you're doing a terminal command, not Python code. So you're like, if you're familiar with Linux at all, this is kind of just Linux terminal commands. And we can do that in Colab, which is cool. Someone said, is Colab free or do we have to pay? So Colab is free. There's a really great free tier that you get access to, I think GPU for like 12 hours a day or something really good. But they have a paid version that I'm actually using right now, and it gives you a little bit better GPU sometimes and access to GPU, I think 24 hours a day. So you don't get cut off. All right, so I'm going to keep going, and then I'll be hanging around to answer any questions. So we'll go through this code, I think, fairly fast, and you'll have an object detector, and then I'll also be hanging around to answer any questions you have. And then again, connect me on the Slack or LinkedIn too if you have anything outside of this workshop. All right, so the first thing we want to do is install some dependencies. So we actually have to install Detectron 2 because it isn't just on Colab by default. A lot of libraries are on Colab by default though, so you don't have to install things like TensorFlow and some other common data science libraries like scikit-learn or NumPy. Those are actually pre-installed. But a couple of things, like if something that you want to use isn't installed, then you can do that using things like pip install if you're familiar with Python. You just have to put the little exclamation point beforehand. And I left this code cell here. It's commented out, so it actually won't do anything if you run it. But if Colab changes the version number of PyTorch in here, then you could run this, uncomment this out, and install the correct version. Because like we don't control our Colab instance, Google automatically just updates it and tries to put like the latest technology in here. But sometimes that can break the other code. So if Detectron 2 wasn't updated to work with PyTorch 1.7 and Colab threw it in there, you could uninstall 1.7 and install 1.6. but by default, it currently has 1.6 in Colab. So here we're going to pip install PyYAML and PyCoco tool. So that's a tool for working with the Coco dataset. And we're going to import Torch and Torch Vision, which are PyTorch libraries to work with computer vision as well. These are just some requirements for Detectron 2. And then here we're going to do pip install Detectron 2. So it just goes to where they have it hosted, and it's going to install pretty fast because most of the requirements are actually already in this notebook. So it can take a minute. And then here I even have this little assert function just saying, you know, make sure the PyTorch is the right version that we're expecting. If not, then you might want to go and install the correct version here. And it's already installed. So you get this little warning message, just ignore it. It says like something wasn't imported on this runtime, but I think everything that we need was imported and you shouldn't have any issues. So now if we do that exclamation ls, we can actually see that installed Detectron 2, this is kind of the version just saying it's 2, but it's a new folder in there. All right, and then here we're just going to install or import some libraries that we're going to use. So we're going to import Detectron 2, because that's what we're going to use. We're going to import some common libraries like NumPy, OpenCV is CV2, and some other ones that we'll see as we use. And just give that a second, and it should be imported. Let me, just real quick question to everyone. I just want to make sure, is everything working for you? Are all the code cells running? All right, cool. People are saying yes. Awesome. Just want to make sure that no one's getting any errors. All right, so importing a data set. So for this project, we're going to use my, say, famous, because I've used it so many times in different talks now, and everyone kind of knows this if they've come to a talk before. And some people even started calling me Goose Guy. So now I'm saying this is my famous synthetic goose data set. And you can totally read more about it. Again, the link is in here. I think it's a pretty fun little talk. It's not quite as long. And you can even just kind of read the GitHub repo. It was really created for the talk, not like a blog post, but you can kind of read it like a blog post too. And then, so we labeled a data set, or you're going to label a data set after this workshop, but I labeled my data set with hyperlabel, and then I exported it to a Coco format. And you can read more about it on the hyperlabel docs. All right. So to get this data set that I trained, I'm going to talk about how to get your own data set in here. But just for this workshop, to make it really easy for everyone, we're just going to run these code cells. And I just have that Goose data set on a GitHub repo. And so we're just going to clone that repo down in here. And while this is cloning, well, it shouldn't take too long. And then we can see that, you know, ls, this is, again, like a terminal command, just listing a directory out. And we're saying, list everything that's in that new directory, Goose object data set. Inside there, you can see that there's a folder for train and a folder for validation. So we have two data sets, one for training our model, and then one that we can use to test our model after we train it. And you could look in there, see if these are all the images. All right, though, but real quick, so if you want to get your own data set in here, I guess I'll get to this. This next code cell is where I'll show you how to get your own data set. So from Detectron 2, we're going to use a function called register Coco instances. And we're going to pass in, we're going to say we're going to call this my dataset train and my dataset val for validation. And then we're going to pass in the path to where that JSON file is stored that came from hyperlabel, and to the path of where the actual images are. And I'll show you how to do that in a second, or how to get your own. So in this case, like we installed this data set just with Git, right? And this makes it easy for the workshop, but most of the time you're going to have your own data set that you want to get in here. There's a couple ways of doing that. So I'm going to go through that real quick. So on the left here, you can see this little folder icon. and you can click on this. And one, you could find your data set in here, like just on your drive, and you could just click and drag it and it would upload into your instance here. And that can work fine if you have like a small data set and you just want to do something once with it. But the thing is, when you restart this notebook, like if you go away for a while, the instance is going to end and then you'd have to re-upload it, and that can be kind of annoying. So what I would recommend doing is you can click this icon. I think mine's already connected to Drive, but you would click this little Google Drive icon, and that'll mount to your whole Google Drive. And then what you can do is in your Google Drive separately, or even in here, you could click and drag once Drive is mounted. So I mounted in my Google Drive, and I can actually now explore it. I have all my folders. I have one that I made for like machine learning, one for data sets. And then so if I want to have a data set that's just always going to be available for me, I would put it in this like data set folder on my Google Drive. And then let me actually find one. I think I actually have under one. I was doing something with pumpkins for Halloween. So I have my cocoa labels here. And then what I would do is just, once you find where your data set is in your Google Drive, you can just copy the path to it. So copy to your instance JSON. I would paste that here. And then if I wanted to go to where the images live, all my images are in this image folder. And I would just hit this and copy path. And then I would just paste that here. So that's, if you know you're going to be working with the data set multiple times, I'd recommend putting it on Google Drive somewhere, and then keeping it that way. And again, just once you do it once, I think it'll make more sense. If it sounds really confusing, it's actually pretty easy. You just hit this Drive button, connects, navigate to your Google Drive, and then find where you saved your data. But in this case, we're going to just stick with that Goose data set and train a model real quick. Someone asked a good question: what's the difference between training and validation? So oftentimes you're going to have at least 2 data sets, if not 3. And you'll have a training data set. That's the data that goes into the model and how it learns, in this case, what a goose is. And then you're going to have a test data set or a validation data set that you're going to give to the model after it's trained to see how accurate it was. So you can actually run it on images that it's never seen before and see how well it performed. Often there's going to be 3 where you have a training data set to do the training, just like we talked about. Then you use a validation data set that while it's training, it can give you some output of how it's doing on images it's never seen before. And then you as a human can kind of make adjustments to some hyperparameters that we'll talk about to make it kind of fit better to the data. And then you have another test data set that it never saw and you never saw while making those adjustments to make sure that it does generalize well on new data. Oh, someone said, how do you separate them? So yeah, there's different ways of doing it. Like you could create some sort of function that would automatically like splice images and splice the JSON. In this case, I did just create 2 separate projects in Hyperlabel, one for validation and one for geese, and you want to label them just like you're labeling regular. Someone said, what is register Cocoa instances? So that register Cocoa is saying we have a Cocoa data set and we want to read that Cocoa data set in so we can use it to train a model. It's just a built-in function from Detectron 2 that makes it really easy to read a data set. Otherwise, and you can build your own custom data set methods in Detectron 2 to read in kind of any type of data, but it has pre-built ones for common ones like Cocoa. So we're going to run this if you didn't already run it and did no output, but we just registered these data sets. And then here, this is a very important step, is you almost always want to take a look at your data to make sure that you read it in correctly, because especially if you're creating your own function to read in a different type of data, instead of just using like the register Cocoa one. Because if you have something messed up, like the reading in those bounding boxes, it could, it might actually not be labeled correctly, or the label might be down here if you did something weird and not actually run the goose. So this is just saying, go look at that train data set and then randomly get 3 of them and then show them, like draw them out over here. And this is what we want. We can see, just 3 random pictures of geese and that the labels are drawn around them and they're labeled correctly. And you could run this again and it'll always just grab 3 random images. Again, Looks correct, looks good to me. Cool, let's continue. All right, so training the model. I'm gonna go ahead and I suggest you do this too. We're gonna run this training cell and then I'm gonna come back and talk about it because it could take a little while to run. So go ahead and just run this. And this is actually us training our model right now. So we're bringing our data in, we're passing it to that convolutional neural network. And now it's starting to learn what a goose is and what are the characteristics of a goose. Real quick, you can see it just gave an output, said there's 302 instances, and then you kind of see some stuff that it's downloading right now. So I'm gonna scroll up and we'll talk about this later. Someone said, will this tutorial be on YouTube? I believe so. I think it's gonna be on AI Camp, I'm assuming. All right, so, and we get this warning when we first run it saying RI heads, it's saying like there's a different incompatible shape. That's okay. That's actually what we're doing, is saying that we're taking weights from transfer learning that was pre-trained on A1 classes. And in this case, we're only trying to predict one new class. So we're saying now we're trying to do just one class prediction instead of 81. So we're saying, hey, there was like a mismatch of like, we were originally trying to do 81 classes. So that's just what that error means. It's totally okay. All right, so talk about this configuration for it. Here we're initializing our configuration. We're just making kind of a variable called config. And then this merge from file, model_zoo.getConfig file, this is actually saying what model we want. So this comes down to, like, if you want to do object detection versus image segmentation, this is what you would change. So actually up here, you even have text for a Cocoa instant segmentation. So if you're doing that polygon labeling and you want to get that pixel kind of perfect prediction of where something is, you would change this text to this. And I linked to the whole model library up here. So they actually, or model zoo, as they call it, they actually have a whole bunch of different ones. So if you want to do like the pose detection, image segmentation, or object detection, there's different models for that. And so this is what we're doing here. We're just saying, hey, give us the Cocoa detection. It is trained on faster RCNN, so it's going to be pretty accurate probably. And that's what that line is doing. And then here we're saying there's a data set for train, and we're passing in my data set train that we created before with that Cocoa registration. Don't forget, if you are changing this at all, don't forget this comma at the end. It makes it a tuple and expects a tuple format. If you don't have that, it'll throw an error. Optional, you can create, like I was saying, if we had 3 data sets, you could create like a test and validation data set that as it's training, it could also be applying to a data set that it wasn't learning from, and then you could see how accurate it is on that data set. Number of workers, you'll see this in like PyTorch, where you can adjust for how many processes there are for like loading images in. So if you had a whole bunch of GPUs and you actually want to like say how many to run on, you can do that with this. And then this is an important part too, is this model.weights. What we're saying here is, you'll see this is exactly the same as the model that we chose, because there's a pre-trained model that has all the Cocoa dataset weights from those 81 classes. And what we're saying here is don't start from 0. We're saying, hey, let's start our training using transfer learning. And we do that here. So if you didn't have this line, it would take a lot longer to accurately train a model. And then here's solver images per batch, images per batch per GPU. So you can kind of scale that up, again, depending on how many GPUs you have. And then this is an important thing to possibly think about changing when you're training your own model. It's called a learning rate. And this is how, this is something that the deep learning neural network uses, kind of like how it optimizes and learns. And you'll learn more about this if you go through like a deep learning tutorial. But essentially, like, you can go lower and higher. And if you are having a hard time, like your model has a hard time understanding, in this case, what a goose is or something like that, we could try going a little bit lower, put another 0 here or higher. Most of the time, you'll probably want to go a little bit lower, and it will just take a little bit longer to train, but some parameter to think about possibly tweaking if you're having issues. 001 is usually just a pretty good one to start with, and for most common types of data, it's probably going to do okay with. And then this is another one. This actually might be more important for you to know about changing, as when you're creating your new data set and feed it into this model, what this parameter does is say how many times is it going to loop through and learn from that data set. So in this case, we fed it that 304 instances of geese. It looked at that 300 times to learn from it and made some adjustments every time. And that's not that many iterations. So in this case, it's going to work pretty good because the geese are pretty similar to each other, right? There isn't a ton of extra stuff to learn. Like if it learns from one goose, it's probably learning similar things from another goose. But if you have a more complicated data set, you'll probably definitely want to up this iteration. Like you could go to 1,000 or a couple thousand. So something to think about there. And then images or ROI stands for region of interest. So they're just saying how many regions of interest, how many instances of a goose will be there. It'll read in 32. And then this is also another very important parameter. And I forget to change this all the time if I'm using like a script I already made and then training a new classifier object detector, is that here, in this case, we're only detecting one new class because we're only detecting geese, right? But if we were doing geese and ducks, then we would change this parameter to 2. If we're doing geese, ducks, and elephants, it would be 3. So whatever, however many classes you're trying to predict, you need to change it to that number. So someone talked about doing lamps. If you're doing like a lampshade and like a switch and the pole, then that would be 3, and you would want to make sure you change it to 3 here. So very important, and I definitely have forgotten many times. And then you look at your output and you're like, why isn't it doing this thing? All right. So did people hit train? Mine's already done training. Yours might have taken a little bit longer because one thing about Colab is it will randomly kind of choose what GPUs are available. And I do have the pro version, so I probably got a little bit better GPU than some people. But for me, doing 300 iterations only took about 2.5 minutes. It's possible that yours is still training or that it just took longer to train. But did anyone finish training their model? Someone said, how can you implement a validation loader? Great question. So I think I even linked to that in here. Like I just didn't have time to do it. I think if you go to this tutorials config, it actually talks about it in the documentation. All right, I'm gonna wait a few more minutes for people to finish training. Some people, again, it's just probably just bad luck of the draw of whatever GPU you got, so it might take a little bit longer. But I'll go through all the code, and then once it's finished, just run all the code cells, and it should totally work too. Someone asked, what is a validation loader? So when I talked about having those 3 different data sets, most commonly, like if you're actually doing this for a like production model, you'll want to have at least 3 data sets like that. And what's going to happen is as we're training here, like here, we're seeing that it's saying like losses decreasing, which is usually something you want. And often you'll have something like accuracy. Actually, I'll load this next cell. And the thing is, like on your training data itself, it's almost always going to improve accuracy because it's seeing those images so many times and actually learning about those images. And so it should do a good job of predicting them. But what a validation data set does is it's a separate data set that it didn't learn anything from. But it as it's training, like every few epochs or something like that, you might want to have it run predictions on that validation data set. And then you, as a human, can see that output and see that, oh, well, the accuracy was going up on my training data set, but it's not going up at all in my validation data set. Then you might want to do some changes to your model. So I was asking for some more resources. There's a lot of resources at the end of this notebook, and so this is a little bit over your head, which is totally cool. But I still think you'll learn a lot. Like go through it, go through other resources, and then as you go through more the even more intro tutorials, this will all kind of click. Yeah, there are some good resources at the end of this. If you scroll all the way down to the notebook, there's some good places to get started. Or AI Camp has their course that's like the deep learning for computer vision. And I think in their curriculum, I looked at it, it actually goes more into like deep learning and everything because you can only do so much in like a 2-hour workshop. So this is called a tensor board, and this actually just kind of looks at your output as your model was trained. And so here you can see like class accuracy was going up. That's what we want. And false and negatives are going down. And that's what we want. So someone said TensorBoard did not work here. And I've had a couple people say this before. And I don't know how to fix it. I'm not sure if it's like a Google thing or what. But I have heard a couple people say it doesn't work, and I don't know why. But it's fine because you don't need the TensorBoard to work. As long as everything else is working, you should be good. But TensorBoard should give some sort of output like this. But I have occasionally seen, for whatever reason, with people, it just won't spin up in Colab. All right, so now we have our trained model. I know some of you still might be waiting. I'm just going to go ahead and talk through this, and still let me know if they're done. Okay, so we can just look. We actually have an output folder now that was created when we trained our model. I actually go in here, can look at this output folder. We can see this model path or model final path. That's our trained model right now, which is cool. All right, so now let's use our trained model so we can actually run it on an image and a video. So again, we're just going to set up that config again. It's kind of the method of how you do it in Detectron 2, saying config. And then this selection here has to be the same model architecture that you trained your model with. So whatever you chose to train your model with up here, make sure that you choose it in that configuration down there. So if you change it to the image segmentation one, you'd want to change it to the image segmentation over here. Otherwise, you'll get errors. And then here we're saying our model weights, instead of like before when we downloaded the weights from the same path as our architecture, now we're saying our model weights are equal to the actual model we trained inside of this output folder. And then we're adding a test data set that we can actually run some metrics on. And then again, here's the number of classes we're trying to predict. So again, make sure that this is the same that you actually are trying to predict. So in this case, again, it's just 1 because we're detecting geese. But if you're doing ducks and geese, you would change this to 2. And then this region of threshold. So this is saying don't predict it unless it was like 90% sure that it was a goose. And you could change this lower. You know, if you're okay with like a 75% threshold, you could change that number here. And then we're creating a predictor variable that we can use. So we'll run this code cell, and then go ahead and just run this next one, and I'll walk through. But you should get an image like this. And this is an image that it's now running a prediction on. So let me know if you get an image like this. What we're doing here is we're reading in an image path just from our validation data set. We're using OpenCV to actually read that image in. And then we're running the predictor that we just made, the Detectron 2 predictor, on that image. And we're getting outputs. And then the outputs, we'll look at that in a second, but the outputs will be kind of like the coordinates of how to draw that bounding box and what class it belongs to. And then this visualizer is just something built into the Detectron 2 that we imported. And you see this slicing in Python. This is actually just reversing the color in the OpenCV image, because OpenCV actually has the reverse color order. So instead of RBG, like most people say, it's like BGR. So you have to reverse the color, otherwise it would just be weirdly colored image. And then we're just saying the scale is going to be 50%. The metadata, so this would be the labels, like saying it's a goose or not. We're just getting from our test data set that we created up here. And then we're drawing out the image. And yeah, so someone said it's the same image. We're directly looking at one image path, not at a random image. So it should all be the same image. And then let's look at the output. So this is actually the important thing, is when we made the prediction, when we passed this image into the predictor, this is what's being returned. So we look at those outputs. We can see that there's a couple things in here. One, it says, number of instances, saying there's 2. That's correct, right? Like there's 2 geese in here. And then it says like image height, image width, just some parameters about the image. And then this is the real important part, is in these fields, we have something called prediction boxes, pred boxes, and then the actual boxes here. And this is an array of the coordinates of where to draw that rectangle at. So it's saying, you know, it's from here to here to here to here. That's where I think a goose is. And then it also gives the rectangle for the other goose. And then it also has the confidence score. So how confident it is that it's a goose. In this case, both of them, it's almost 99%. And then the predicted classes. So it's saying 0 and 0 because we only have one class. Python, like most programming languages, it starts indexing at 0. So if we had goose was the first class and a duck was a second class, you know, 0 would be a goose and a duck would be 1. And that's really cool. This is actually the really important stuff behind the scenes that like drawing out is visually great for us humans. But if you actually want to do something in some program, you're actually probably going to use data from here. And you can also create your own visualization library. So we're using a visualizer from Facebook that can kind of draw these little lines. But oftentimes, I actually want to do a little bit more custom visualization. So I'll use OpenCV, grab these coordinates from this output, and actually draw them myself with like the OpenCV library. And then here, like here's actually, we're going to make something that could actually be already super useful. We're just saying, making a variable called object count, we're saying is equal to the outputs that we got from the prediction. And then we're saying print detected. And then we're just saying, you know, concatenate a string of object count and saying how many objects were detected. So, so here, like this, you can see that this is probably already could be a useful application if you wanted to just monitor how many of something there are in an image or in a video stream at a time, right? Like if you're detecting how many people are there just on every frame, you could totally do that already just using something like this, which is really cool, right? And then here's kind of like the behind the scenes stuff too, right? If you had coordinates for all the polygons, that's where then you can write a little separate program saying if polygons overlap or anything like that, then do a new classification, like when we saw with the mouse overlapping with a piece of food, then it's like feet. All right, and this just runs on another image. And this image is so cute. Look at these cute little baby geese. They were having babies and it was adorable. It was great taking photos of them. But one thing to notice here is, well, if you actually looked at all the data set, we never trained it on these baby geese. We only trained it on the big goose. But we also had never had any images that had baby geese in it in our training data set where we even had, like, if we gave this whole image to our model with just this goose label, it would have learned that these baby geese probably are not the things we're looking for, and it wouldn't be predicting them with such a high accuracy. But we didn't do that, and it sees that, well, there is something here that's like kind of like bird. It maybe has some of the similar shapes, so it thinks it's a goose. And so this is a big problem, and I talk more about it in the other talk that I linked to on GitHub about how to overcome this and think more about that way where if you knew that you were going to have baby geese in your frame and you don't want to have them predicted, you would want to make sure that this is part of the training data set and then only label what you want predicted, and the model will then learn what you're looking for. So it's really interesting to think about because you think that, oh, I can just give it data and it's going to learn that data really well and it's going to be fine. But it matters so much about giving data with the correct environment or correct other like objects that are going to be around it when you're running predictions. So evaluation metrics, we'll just briefly run these. I just threw them in here because it's useful when you're actually building your own model and that Detectron 2 hasn't built in. So we're using that validation data set that we had separately so that we can say, well, how good did our model do, or how well is our model doing on new data? And so we'll feed in data that it never saw. And then you get some metrics here. Oh, I linked to a good post. You can click it because you have the notebook, but I'll share it in here too. So these are some good posts explaining in more depth, like the evaluation metrics. But in general, you have these kind of like average precisions. And here we're almost about 60%. I think with this, we'd have much higher, except for in our validation data set, as that example that I wanted to show you. We have like these baby geese in there. And so, you know, it got this goose right, but it got all these wrong. So the average precision is going to go way down if it's getting stuff wrong. in the validation data set. And then there's, again, you can read about how this does it, but it's like average precision with different kind of variations of looking at the data. So really good when you're actually training a model and you want to see how well it's doing. All right, so we're almost done. We're going to run detection on a video, and then you'll have something really cool to like show to people, especially if you do this on your own data set and have a video of running your own object detector. I think it's a really fun thing to like show and post about. Like a lot of people takes a lot longer to get to this point of like you're building your own object detector. So having that as kind of even just like a portfolio piece or something really fun to show is really powerful. So here, and you don't need to do this all the time. If you have your own video, I'll show how to run it on that. In this case, though, I have a video of a goose on YouTube, and it can be kind of fun to get some other videos from YouTube and just download them to run object detection on. So here, this is just displaying that video. You can see that it's just a goose here. And we're going to run object detection on this. So here, this is installing dependencies. Again, just if you want to download a video from YouTube, you don't need to do this on everything else. Oh, someone asked for the Colab file. Yeah, let me give you this. Here you go. And you're gonna you should be able to run all the cells if you came in late, and you know, get all the results. Here, we're just saying we want to download that YouTube video. And then here, we're using some library called FFmpeg, which is actually really useful. And we're just creating a 6-second segment from that video. And then we're calling that video a video clip.mp4. So this created just a 6-segment clip. You don't need to do this all the time either, but it's really useful when you're testing stuff out. Like if I'm going to train a model and I want to make sure that it's working, instead of running inference on like a whole video for, you know, a minute or 5 minutes or something, I can do like a 6-second clip just to make sure that it's working the way I think it should be working. And then here's where we actually run the video. So run it on a video. We import the video visualizer from Detectron 2 and the frame visualizer. Then here we're extracting video properties. So we're just saying CV2, which again is OpenCV, you know, get this video clip. That's the clip that we just made. But if you want to do it on your own video, it's the same thing with datasets. You can hit this little folder icon. You could then, again, like drag and drop a video up into your instance, or navigate to where your video is on your drive. And again, if you know you're going to run it multiple times, I totally encourage you to just connect to the drive. And then, you know, you could get, like, I have an input video here, and I would just copy this path and then change this path. You know, instead of running it on this video clip, run it on this. And the path just looks like this if I copy it in. So it's just saying, you know, go to a drive, go to my drive, and get that MP4. Really useful. I'm going to go ahead and actually run this as I talk through the code, because it can take a little bit. You see some output, saying what percentage it's done. So we're getting video properties with OpenCV, like the width, the height, frames per second, number of frames in the video. And then we're making a new variable called video writer, and then using OpenCV to essentially, we want to write out our frames that we're going to run detections on into an MP4 format. We're initializing a visualizer, so that's the video visualizer we imported from Detectron 2. So we're saying that we could give the visualizer a new frame and predictions, and it would draw those out for us. And we're getting the metadata. So like in this case, really, we just want the labels, like how many labels are there, or how many classes are there. In this case, it's just going to be a goose. But again, if you had a goose and a duck, you could get that from that test data set. And then this is the actual function of running the prediction on every frame in the video. So it's just saying, you know, while there's still frames left in this video, get outputs from running the predictor, just like we did on the single frame, except for it's doing it for every frame in the video. And then instead of that slicing method that we saw before, there's actually a built-in method in OpenCV called RBG or RGB to BGR. Like I was saying, OpenCV has reverse like red, blue, green color schema. So you have to reverse it back and forth to get the correct colors. And then here we're saying that new visualization is equal to this v.draw instance prediction. And that's our visualizer that we imported. We pass in the frame so that each, again, right, like a video just becomes a frame per like second or whatever the frame rate is. And then we want to run a prediction on it. And then we want to get what those outputs are, which is what we did up here. And this drawing method, we pass in that image and then we draw or then we also pass in where those bounding boxes were located and then draw them out. And we're just making visualization. Again, this is really just reversing the color schema. So when it outputs, it's going to have the right color. Otherwise, it'll be a weird color just from the way OpenCV works. And then we're just returning or yielding our visualization out. And then, so here, this is actually where we call that function run on video. And we're just essentially saying for each frame that was in that video, write it out in an MP4. And then this just closes out kind of the OpenCV video methods. And then run this last code cell here. This will automatically just download our out.mp4 file. And while that's downloading, just quick note. So we'll see in the video actually that, well, I'll talk about this actually when we have our videos to explain it. But that's kind of the last of the code portion of this. And the most important thing, like I was saying, is really just keep learning. You can download Hyperlabel, join me in the Slack to ask me questions or LinkedIn. And I will be catching up on chat shortly. I'm sure there's some questions in there. There's all the links to everything we talked about, including more links to like the paper and really good articles actually explaining them in a more friendlier manner, as well as like some other resources that are better for maybe getting started or beginners. And I'll just copy most of the relevant links you'll want to put in the chat. And here, so our video downloaded. If I open this up, hopefully everything went well. And we can see that it's doing object detection on these keys. And it's pretty confident. And so one thing I wanted to note about object detection versus object tracking. So here, Facebook Detectron has very light object tracking built in, where object detection, we're drawing rectangles around each instance in the frame. But in here, you can see that it's also keeping this random color assigned to the goose. And it's doing that by understanding that like this goose didn't move very far from where it was. So I think it's the same goose as the previous frame. And so it's doing a little bit of object tracking, and it can actually keep the same color associated with it. But if you have, like if a goose is running pretty fast or something like that, it wouldn't be able to do that just with the way that Detectron 2 does it. It's not really meant to be a robust object tracking algorithm. And so that's a whole different topic you can dive down into. Once you have a good object detector, then you can implement something like object tracking, where you want to keep track of exactly the same goose and where it moved to from frame to frame, which is a much different problem. All right, I'm going to catch up on chat. Please let me know if you have any other questions or something didn't work for you. All right. And if you were able to get this video download and actually have an object tracker work. So if you did, that's pretty awesome. And if you never did computer vision before, I think it's awesome. You already built a object tracker in just about 2 hours, which is really impressive. Someone said, could we possibly use this code to run on a computer, not Colab, like using our own terminal and Python text editor? Absolutely. So the thing about Detectron 2 is I think it might be only available for Linux. It might not be able to install locally on Windows unless they changed that recently, or there might be a way around it that I've never done. But yeah, anything like TensorFlow and PyTorch and stuff can also work on Mac and Linux and Windows without much requirements. So it's actually pretty easy to install those things locally. And then you could install just or write in Python scripts or use a Jupyter notebook locally. I do a lot of stuff locally, but this is such a perfect medium for something like a workshop where everyone can just go in. You can have things pre-installed, and it's just an easy flow. Oh, and someone else I think brought up a good point in there. So, oh, and they also said that Detectron 2 is Linux. Oh, and Mac OS. That's cool. But yeah, so having a GPU can be pretty important to actually do the training. And I know not everyone has a GPU. That's why Colab's really cool too, because it's a nice free resource to do GPU training. But yeah, if you have your own GPU, then you can do training locally. And I do quite a bit. I have like a gaming computer with a 2080 in it, and it's really good for a lot of just kind of hobby applications. So I said, how does the B-box evaluation work? I saw it uses it for checking how accurate the model is. Yeah, so what it would do, kind of like we talked about with these images, is it trains on the data, and then it looks at the data again, and it'll try to make a prediction on it, being like, am I learning what the right thing is of a goose? So if it drew a bounding box over here and not on a goose, or over here and on the geese, it would get some penalty saying, no, that's not correct, because on our training data that we have, we could tell that this wasn't a goose, only these two things were geese, and it would get some sort of penalty from that. And then hopefully adjust some parameters, and then the next iteration learns, okay, this isn't a goose, this isn't what they're looking for. Okay, only this is what they're looking for. Someone said, do you have an example of object tracking, maybe another Google Colab? I don't have a Colab set up for that yet. But if you Google object tracking, you'll probably find some good resources. One of the ones I linked to, actually, PyImageSearch, they have a tag, because it's kind of like a blog format. They have a tag for object tracking, and I would look at there. And there's a whole bunch of different approaches to that problem too. So it's kind of like a whole nother really deep dive you can go down to. But essentially, you're trying to say, make a prediction from what frame or like what object is still the same object per frame. And so it often comes down to being like, okay, how do I think about, like, if this goose moved over here and this goose moved at the same time, you could think of it being like, well, what's the closest previous label or something, and then assign that label to it. It's an interesting problem, and it actually gets pretty complicated really fast. Like if your data set is changing in size all the time, like if the goose is coming to the camera or coming at an angle or something like that, it can be a lot harder to keep track of something, versus if it's just like a clean overhead shot of something and it's always the same size going in the same direction, it's a lot easier. Someone said, tried to implement object detection using SSD on Keras and TensorFlow, and it was really hard. Detectron 2 makes it so simple. Or maybe it was your explanation. Any such wrapper, simpler library you know of using TensorFlow and Keras? So I'm not sure which implementation you did in TensorFlow, but they do have a object detection API. Just Google TensorFlow object detection API. And it's not as easy. I don't remember it being as easy as Detectron, but it was doable. It wasn't crazy hard. And actually, the other talk I linked to, I don't go into like a tutorial like I did in this one about how to do it, but I do talk about it a little bit, I believe. Where's that talk? So you might want to go look at this. I think I even linked to some good resources. At the time, the object detection API was only available in like the TensorFlow 1x, but now I believe I just saw an update the other day that it should work for TensorFlow 2 now. I haven't tried it yet, but that's actually my weekend plan, is to try object detection with TensorFlow 2 with the object detection API. So if you try it before then, let me know, Kennedy. I'd love to hear about if it was easy or hard. And I think I've seen some recent articles around it. So if you Google it, I bet there'll be some good modern stuff. Some of this is really cool. I'm excited about computer vision now. I hope so. The main goal around me doing these workshops is I really hope that I can get people excited about computer vision and make it a little bit more approachable. So I know that there's like way more that you'll probably need to learn or that you'll want to learn to really understand what's happening behind the scenes. But I think that you can see that you can label a data set and train a model to do something really powerfully in not that much amount of time. I mean, you're going to run into issues, I'm sure, but you'll overcome those and you can make awesome applications. Saying great workshop. Thank you so much. I try. Oh, someone said presentation slides in school. You need access. Okay, yeah. After this talk, I'll make them public. Sorry about that. You want to use a video surveillance for object detection or tracking? Are there examples in COCO datasets along with transfer learning? In other words, I don't want to start from scratch to leverage existing images and weights. Yeah, so I mean, if you're doing surveillance video and you just want to detect, is there a person in there? COCO does come pre-trained with like detecting people, and you could try that and see how that works in your application. Otherwise, you can use a pre-trained just weights like we did here, but then just label examples of what you're trying to detect. So it said, any tips on how to deploy a detector on 2 model? Use our platform sense. No, so like that can be a whole another giant like workshop thing too. I think that I want to say the AI Camp one goes into that a little bit using like GCP, Google Cloud Compute. There's a whole bunch of different methods of doing it. But once you have that model saved, like you can make a little Flask server that then also imports that model, and then you have someone like, there's so much that goes into deployment, like how's the data getting into it as well? Like, is someone uploading a image? Is it looking at a video stream? There's a lot of stuff that goes into it. But you could do something with like Flask or Fast API? I forget. There's another one that's really good for kind of machine learning models that you can create a quick API for. Yeah, someone said they joined late. Yeah, you go through the Colab, and I will make those slides accessible. And again, just let me know if you have any questions. So again, the best place to reach me at would just be in either this Slack channel or LinkedIn. I'm pretty active on LinkedIn as well. Awesome. Looks like people saying they had fun. Yeah, does anyone have any questions about like labeling or anything like that? I know, again, that's something that's often not covered a ton in other places, and it is really important. So like I talk about this talk a lot through this, and you could go through it just to kind of learn more about, how to overcome a limited data set or anything like that. If you have any questions, let me know. I see Bill's back.
Hello.
How's it going, Bill?
Great, thanks. Good. I see that's a lot of questions, discussions. It's great.
Yeah, I was just gonna show real quickly. So one of the parts of this talk was saying how you could train an image classifier and it could recognize something like a goose really good in the context of a park. But as soon as I try to run the classifier in my living room, it does a really poor job of thinking like it's very confident that I'm a goose, because we did a good job at telling the model what a goose was in that context. But we didn't do a good job of telling what the goose was, or what wasn't a goose. And so one quick way of overcoming that, which is related to, I think, a question asked in the chat, is that you could create like your own synthetic data set where here I put geese in my living room with Photoshop, not in real life. Though that would be way more fun, and then relabeled it in only 10 images. And then when I ran the detection in my living room again, it no longer thinks I'm a goose or that my chair is a goose or anything like that. So some way to quickly overcome kind of some data set limitations can be done this way.